Welcome to this learning module on Retrieval-Augmented Generation, or RAG. In this session, we'll explore how RAG combines the power of large language models with external knowledge sources to produce more accurate, up-to-date, and factually grounded responses. Designed for AI practitioners and developers, this resource will walk you through RAG's architecture, implementation steps, and real-world applications, all while keeping things practical and accessible for students. So, what exactly is Retrieval Augmented Generation? RAG is a framework that boosts large language models by pulling in relevant information from external sources before generating a response. This means the model doesn't rely solely on its internal training data. Instead, it retrieves up to date or domain specific documents to ground its answers in real facts. This approach significantly reduces hallucinations, those confident but incorrect statements LLMs sometimes make, and leads to more reliable, accurate outputs, especially in technical or fast-changing fields. RAG offers several key advantages. First, fact grounding ensures responses are tied to verified external data, not just patterns learned during training. Second, knowledge freshness allows access to current information like recent news or updated guidelines that the base model never saw. Third, domain adaptation lets you plug in specialized knowledge, say from legal or medical databases, without costly retraining. And finally, it's cost efficient. You enhance performance using existing models and data, avoiding the expense and complexity of fine tuning. The RAG system has three main parts. First, the user asks a question. That query goes into the retrieval component, which uses an embedding model to convert it into a vector. This vector is then used to search a vector database storing pre-embedded documents. The top matching documents are retrieved. Finally, those documents, along with the original question, are fed into the large language model, which generates a grounded, context-aware answer. This modular design keeps retrieval and generation separate yet tightly integrated. Let's break down the two core components. On the retrieval side, we use embedding models to turn both queries and documents into numerical vectors. These vectors live in a vector database, enabling fast similarity searches, usually via cosine similarity, to find the most relevant chunks. On the generation side, the LLM receives a prompt that combines the user's question with the retrieved context. It then performs inference to produce a coherent, fact-based answer, which may be further formatted or filtered before delivery. Together, they form a powerful pipeline. Implementing RAG follows a clear four-step workflow. First, you ingest your knowledge base PDFs, web pages, or databases, and split them into manageable chunks. Each chunk is passed through an embedding model and stored in a vector database. Second, when a user submits a query, it's encoded into the same embedding space. Third, the system retrieves the top K most relevant document chunks based on vector similarity. Optionally, you might re-rank these results. Finally, the retrieved context and original query are combined into a prompt that's sent to the LLM to generate the final answer. To get the most out of our egg, several optimization techniques can be applied. Query expansion improves recall by adding synonyms or related terms to the original query. Re-ranking uses more precise models like cross-encoders to refine the initial retrieval results and boost precision. Hybrid search combines keyword-based and semantic methods to capture both exact matches and conceptual relevance. And metadata filtering lets you narrow results by attributes like date, source, or category, ensuring context stays relevant to your specific use case. These strategies help balance speed, accuracy, and relevance. Despite its strengths, RAG comes with challenges. Latency can become an issue. Retrieval adds time, so balancing depth and speed is crucial. Context window limits in LLMs mean you can't feed in too much retrieved text. Smart chunking and selection are needed. Relevance drift occurs when retrieved documents seem similar but miss the user's true intent. And evaluating RAG systems is complex. You must measure both retrieval quality, did we get the right docs? And generation quality, is the answer correct and fluent? Addressing these requires careful design and iteration. Here's a key insight to remember. RAG grounds AI in reality without retraining the model. This captures the essence of why RAG is so valuable. Instead of expensive, time consuming model updates, you simply connect your existing LLM to a dynamic knowledge base. It's a pragmatic, scalable way to keep AI responses accurate, current, and trustworthy, making it ideal for real world applications where facts matter. To wrap up, here's how you can move forward. First, explore RAG frameworks like LangChain, Llama, Index, or Haystack. They simplify implementation. Second, experiment with different embedding models from providers like OpenAI, Cohere, or sentence transformers to see what works best for your data. Third, build a basic RAG pipeline using your own documents. It's easier than you think. And finally, don't forget to evaluate. Track both retrieval relevance and answer quality using metrics tailored to your use case. Start simple, iterate, and let external knowledge empower your AI applications.